CTO and President of Andes Technology, who will present transforming model computing with RISC-V.
Andes Technology CTO 兼社長チャーリー本面数様による RISC-V による現代のコンピューティングの変革、よろしくお願いします。
Thank you. Thanks for everyone coming. I'm the first talk after lunch. So I hope that besides lunch, everyone's body has room for my talk. Okay. So transforming modern computing with RISC-V. We know RISC-V targets for all computing devices. And in the recent past several years, RISC-V has been quickly adapted by many applications. So I'd like to take this opportunity to examine 4 key modern computing technology enabled by RISC-V, the ecosystem, and certainly Andes. A quick introduction of Andes for those who don't know. Andes is a quite young company. Just in 2 weeks, we're going to be 20 years old. We have been doing processor IP for that long. And our product have been used from endpoint, edge, and cloud. Andes is very active in RISC-V International and also RISE. And we are founding and also premium member for those 2 organizations. So some quick number, Andes has over 30 RISC-V processor IP, over 400 customers, about 500 up and down employee. Our ID has been used by more than 100,000 engineers. And our customer together already ship, we call Andes Embedded or Andes Pulse SoC, for over 16 billion. So quickly looking at Andes lineup. So Andes cover a wide range of products from the compact series 2-3 stage pipeline to 25 series, 27 series, 5-stage pipeline, very compact and enhanced with memory performance on the 27 series. And to 40 series is the 8-stage pipeline, dual issue, superscalar. And all the different series, we cover kind of different category of the sort of application, from embedded control to compute acceleration with simply DSP or all the way to vector computation. And all the A-core basically supporting Linux. And we also have a product line support functional safety. And on the top X60 series, it's a full feature. So it's auto-order, Linux, multi-core, everything. So we have a couple of different series there. So we're going to talk about basically their application mostly, so people know how our core and also RISC-V technology has been used. So most people probably know the market research company called SHD Group. This report is from early 2024, so it's for 2023. We are waiting for the report to come up. I think probably in another couple weeks or at least in a month, it should come out for 2024. But so far, so for 2023, basically have about 2.8x growth in the SoC, RISC-V SoC revenue growth. And the projection from 2023 to all the way to 2030 is 15x. That's pretty huge. But you can plus minus the number. And also, they do the research on the RISC-V IP market in 2023. And Andes has over 30% of market, which is number 1. And we very eager to wait to see what the result will come out. So what does Andes processor being used for? So everywhere. So mobile, which is application surrounding the smartphone, Wi-Fi, Bluetooth, touchscreen controller, storage, and so on. And talk about storage, from SD card all the way to enterprise SSD, data center SSD, or our customer there. And also 5G networking, general purpose MCU, MPU. About 3 years ago, we had the first processor certified by, fully certified by the HGS tube. So we officially enter automotive market with a functional safety core. Now we have 3 now. And last, actually, is a large-scale AI machine learning, which we're going to spend a lot of time talking about that. So here you see a couple logos there. We will cover them later. And so a couple more direct applications, like AIoT, wearables. So Renesas is using our core for voice control, ASSP solution, like D25, 5-stage core with DSP. And also their general purpose MPU running Linux using X45MP, used by ASUS IoT division doing the Tinker5 single board computer there. So it's pretty interesting. And also our core has also been used by a smartwatch with long battery life. And it's our core D25F is used as a main processor. So if you just do a normal use, the battery can sustain for 4 weeks. If you use it for like running like to 20 kilometer in 2 weeks, it can sustain about 2 weeks. Yeah. So that's a watch I wear in my hand. So I buy one. All right, and also some example of the use. So enterprise storage used by our customer Phison, which is X1. I think they're using 33 of our processor and 25F. And also HPs use our processor to do their multi-camera panorama image processor. And also interesting is in the Phison case, they're also using Antis custom extension to extend the process capability. Okay, all right. So back to our main theme. So key computing technology enabled by RISC-V. I think I list is 4. So AI machine learning acceleration, which is kind of enabled by RISC-V extension, like vector extension. Also RISC-V allow custom extension, so you can add extension to your application. Especially use that to interface with your NPU. And certainly the software, end-to-end software stack, that also can help a lot by the whole RISC-V ecosystem. And embedded and real-time processing, code size important when you embedded the code, like a couple hundred kilobyte to your MCU or like megabyte, even possible. And efficient device control and interrupt and so on. And also functional safety and security. I think ISO 26262 fully compliant. And RISC-V has something like RERI, which enable the error reporting mechanism that's also quite relevant here. And for security, we're going to talk a lot about that. That's one of the most focused discussion community in RISC-V. And also general purpose packaging processing, supporting Linux, supporting Android, and also rich applications. So those are what enabled by RISC-V. So we're going to talk into each one after this. So certainly for AI, the most interesting one I think is starting by about 2.5 years ago. ChatGPT kind of come up. And then about a little more than a month ago, DeepSeek come up, have some interesting result. But I think the edge going to be the most even bigger opportunity for AI machine learning, like robot, like autonomous driving, and so on, surveillance, and okay. All right. So first one is large scale, well, AI machine learning acceleration, that in general, RISC-V has a lot of things to contribute, but here I focus more on large scale. So the popular SoC architecture for large scale AI machine learning is called C of PE. So those PE either mesh connected together, like Meta's MTI, we're going to talk about that later, or multi-cluster hierarchical way to connect them together. But the core of computation happens inside the PE with processing element. And there's 3 tiers of acceleration inside the PE. The first one is obviously matrix multiplication, like You can have hardware solution, like some people call MPU or DLA. So they're kind of away from processor, but in order to make them efficiently integrate into the rest of the computation, a lot of customers we see, they like to connect them next to processor. So custom extension is really useful to enable that. We'll see some example later. And also in RISC-V, now the two task groups are looking to metric instruction, like IME and AME. So RISC-V is kind of right after that. And also after metric multiplication, there's a lot of nonlinear function nonlinear operator like softmax, sigmoid, Jelu, Selu, and so on. There's going to be new name come up because AI algorithm keep evolving. So new algorithm keep come up. So I don't think any of them going to become standard instruction for the RISC like RISC-V. So, but RISC-V offer a very good mechanism that is custom extension. And this we call it ACE, automated custom extension. We fully utilize this. We know custom needed, so we provide a framework to help custom to do that, to add that those native operator with hardware to the processor. And then once you have that, there's still going to be a lot of small parallel here, they are not regular. You don't want to do that into hardware. Maybe doing hardware would not doing better. So with that, RISC-V has a very powerful vector extension, which can go as wide as you want, right? So right now I see the market like 2K bits, 4K bits, and so on, instruction per instruction to process that much of data. So that is to catch all the remaining part and future-proof. So once your silicon is out, without this, any new algorithm change, like for example, DeepSeek come out and you cannot run it, right? And certainly with this hardware, you need a lot of AI software stack to fulfill it. Yeah, in this part, we actually been in the quite revolution. So we starting from the long time ago, AX25-V100 as a weird name, but that's the first project used by Meta. And then we moved to 27V. So those are already on production. And X45MPV is the latest one, which already on production. Many customers, I think over a dozen in the large scale computing. Now we're working on 46MPV, going to come out soon, first half of the year. So it's built on the success of 45MPV and adding more code to it. So 45 is 8 core. Now we're going to move to 16 core, and also widen the VLAN, DLAN, and also enhance our crown jewel ACE for the scalar instruction extension or vector instruction extension. And also, while RISC-V has task group working on metric extension, our custom cannot wait. So we already started our this metric extension. So then we look closely to the RISC-V task group and to see how we can align that as we go. And in addition to computation, I think as you go to a large language model, you found that memory performance is very important. So we enhance the load to support single load or store to dual load, or one load, one store, and also enable the private L2 cache. So I think most of the AI accelerator tend to use the DMA mechanism to move data to a close-by memory and to do a processing. But we know there's another category of application where the software might from a third party, so you want to use cache-based programming to enable the porting. So the private L2 is very important to enable that performance. We call thread memory programming. And certainly we will continue to look for the main kind of application, which is using DMA to move data to close by memory, where we continue to enhance our high-speed vector memory. So now it allows multiple outstanding access going out to that memory. So all the order access, all the order data return is very important, even though process is in order. Because when you have, for example, 16 core content for the memory, the HVM, some of them going to go to the same bank, so some of them will come back later. But the other bank, maybe you don't send the request you send later, but there's no container, they're going to come sooner. So you don't want to, you want to enable that to get the best performance. So out-of-order data return is very important. And also, we not just create the HVM interface, we also implement so-called reference HVM controller with up to 16 core and also 64 bank, so that customer can use if they like exactly what we have. But they can also, based on the interface, to do what they want to do. And this 46 MPV is not just one core. It has 4 inclination, it's 32-bit, 64-bit, and with vector and without vector, because vector is quite large there. While the feature we added, like dual roster, private L2, and so on, those will help general purpose application. Right, and so in the software stack side, we have Andis AI runs everywhere. We call Andis Air software stack. From the top, you can take AI model and go through the code, and then pilot doing graph level optimization, pruning, quantization, and then all the way to backend aware optimization. And then either go through the bunch of different library to generate code to able to execute on hardware. So, and there's a couple of things which are very important here, like LVM, for example, is do auto-vectorization for the code which is generated by the ERI TVM path, because not everything is in the kind of optimized operator. They still have lingering code which need to optimize. And ERI part, we enable it so that we do a lot of microkernel optimization, and that microkernel can link to RVB instruction or custom enhanced ACE RVB instruction. So ACE RVB instruction is custom extension instruction, but the format input-output relationship look like RVB and has all the RVB semantic, just like the computation is defined by customer. And they can implement that inside in this automation framework. And we also do auto ERI, because ERI is good, but you need to do a lot of scheduling, tiling based on various architecture. Maybe your memory architecture is still kind of still tuning. So using our auto ERI mechanism, doing kind of search, we have running so far have 4 different models. And Multimedia V1, Multimedia V3, Mobile Bird, and for Multimedia V1 has int A and FP32. It all can get to over 2x speed up over your initial configuration or your tiling strategy. So this is pretty good, because every X here is quite important. And speaking about the code gen, so we have 2 different type of libraries. So any library is kind of more for the MCU RTOS domain, so that, and you probably don't need so-called runtime. You directly generate the code gen. So our NN pilot would generate code and directly invoke the NN library. It's there. So far it has over 200 library there. So it will be quite efficient, because user don't need to understand how our vector pipeline work and how RISC-V RVB instruction like. And for Linux kind of user, for TensorFlow, we directly support XNM pack with a lot of high-level function which optimize there. So certainly optimization is never stopping iteration. So we're going to crank out, like our software development tool compiler, we're going to have every release, in 9 months to a year with a new update. All right, so go back to customers' adoption. So Meta, I think everyone knows the MTI, Meta Training and Inference Accelerator. They first revealed in ISCA, Computer Architecture Conference in 2023, with a paper title like First Silicon Targeting Meta's recommendation system. They're using this architecture with A by A P array, and each P is like the bottom right part. There in that bottom right part, there's a two part, right? In the left part is the NDIS core subsystem, which they're using two processors. One is scalar, in charge of kind of command issuing, and the other one, the vector processor with VLAN, DLAN, both 512. And so that's the first generation. And what's important is not just vector extension, but also we fully utilize RISC-V as a custom extension to implement automated custom extension for customers to create interfaces, register, and to complete new instruction. And we also generate all the necessary file to, for example, enable LLVM compiler. So, like in Meta case, if you haven't read this paper, if you're working on AI, I strongly recommend you read this paper. So their hardware engine accelerator, including metric multiplication, data movement, nonlinear function, and so on. So in order for the AI compiler to do a code gen, they need to make that hardware look like instruction. So going through custom extension is the only way to do that. Okay, so, and their second generation, they're announcing in the hardship last year. So this figure, you can, either you can look at hardship or in the Meta blog, you can find it. So second generation, basically similar architecture, but they enhance more feature there. All right, so I think custom extension, we can talk about it all day. So just give one more example from customer users. So RAN AI is our customer using 45 MPV, and they like ACE a lot. So two things that they highlight. One is called NDIS ACE stream port. The other one is RISC-V. So RAN AI is, other than the software, the AI algorithm, their hardware part is based on computing memory, so SRAM-based computing memory. So NDIS streaming port allow them to move data very efficiently, fastly between CPU vector register and the CIM. And SRISC-V, again, is enable them to create instruction just like any other RISC-V instruction, except they define the semantic. So from hardware perspective, like in our vector processing unit inside the CPU, we create empty functional unit. There they can design any functionality there. And all the RISC-V semantic, like ELMA, like other VLAN, that kind of thing, everything is still there. So we feed in so that they can fully utilize that. So what do they do? So in the talk that they give in last year in this RISC-V conference, they're using Sigmoid as an example, but they also do softmax, SLU, and so on. So what they do using our compiler, so which they can use that environment to design RTL and so on, and then the tool will automatically generate the compiler, debugger, and also simulator to fulfill what they want to do, and then they can, in the simulator part, they can quickly to evaluate the performance to see if that instruction achieves the purpose they want, because all the software tools are already there. And how they can come a little bit later, I mean, RTL part. So it's quite impressive example. All right, so there are several other large-scale AI machine learning examples from our customer. They either based on the NDIS vector processor like NX27V or NX45MPV, or even the one we are kind of working on 46 MPV, already had customers sign up to it, taking your early version. Or using our scalar processor like X65 out-of-order processor, or X45, X25 to do a control task. Because you want to get, for them, 100x speed up. Just take out metric multiplication, just take out all the nonlinear functions is not enough. All the control, all the sequential stuff need to be very efficient so that you can get the speed up you want. So here are quite a few customers using doing the SRAM-based computing memory like Axera, Homo, RAN AI, Tetraman, Fractile. And our company, we are not able to name it yet. And also they're using the same similar environment, custom extension, vector or our powerful scaler for example, light agents use that to work with their photonics, and their customer doing it for cloud, like Reverse, doing the AI SoC for the server, and another customer doing it for others. Okay, so DeepSeek. So DeepSeek, everyone is kind of talk about it every day, especially it come up during our Lunar New Year. So we're supposed to be in a 7-day break, but everyone is kind of doing the email or line to talk about it. So our team quickly put that together. So put the DeepSeek open source version, port it to our 46 platform, and run it. So I asked them to just do some interesting stuff. So I don't know if you can read it. So the bottom, the prompt is that to write a 200-word short article saying that Andes Technology has successfully deployed DeepSeek R1 distill model. And so it, like what it do, right? It will do some reasoning and kind of like thinking about what he's going to do and actually do it. So I'm only going to show what he's thinking. I mean, the other part takes a bit longer. But we already published the one example on our linking page. So if you like to see what it is, so you can use it to write your PR. I'm a little bit too late, otherwise I should give him the whole presentation. So I can sleep earlier yesterday. All right. Okay. Embedded and real-time processing. Like I mentioned earlier, so some of the application, like embedded real-time application, your code need to put in the ROM, or maybe put in embedded flash. So once that into your silicon part, that become your code. So code size is very important. So we have customers doing Bluetooth, Wi-Fi. Their code size is starting from 500K all the way to a couple megabytes. So pretty big, even bigger than the code we license to them. So good thing that recently RISC-V has ZC to bring down the code size by 4.7%, and over the standard AEC, but A is not really helping any code size. And there are also new task group called scalar efficiency is start running for maybe a little over a year. They're looking for more space for reduction. But Andy is very handle this case very carefully, because we know a lot of customers like to get even better than that, so to able to compete with ARM. So Andy, before we joined RISC-V, we have a lot of know-how in terms of code size reduction. So Codance is one of our technology which is patented, so which can bring another 11 to 15% over RISC-V with ZC. So here the benchmark we use from C5 audio codec, M-Bench IoT, and 2 Embassy benchmark, and also kind of Atos running some simple example. So 4.7% for ZC, that's a geometric mean, and 17% reduction, that's for Andis with Codance. Okay, so if you really care about code size, I think Andis can help you here. All right, and also in the a little bit larger system, it's not just purely MCU. So you have you have a bunch of peripheral there. You need to access it or control it, or moving data to the uncached memory, so you can doing DMA efficiently. So multiple outstanding access to the uncached and also device space is very important here. And some of our customers take it even further. So they're using ACE to create the instruction which has custom port to directly connect to their hardware engine. So like this Phison example, there are many different engines, and each one has one processor with special instruction connect to it. So you don't need to send like 32 bits or 64 bits data over the bus when you need to write many of the control register before you can start the operation, right? So you can have 128-bit, 256, or even any number. And from the ACE instruction directory in one cycle, you can initiate the operation. And so multiple ascending access and also ACE support is pretty much supported by all the NDIS core family. Now next is interrupt handling. Interrupt is very important certainly for real-time system. So for RISC-V, there's for scalar, a single core, there's a click core level interrupt controller. And when you have multiple core, click kind of a little bit redundant, so there's a prick. But the problem with prick is it doesn't allow you to do vectoring, vector dispatch, and there's no priority preemption like what click has. And this kind of enhanced prick with this feature. So customer in the multi-core real-time system can use this vector prick to get the performance. And also some customers want to take it further. When interrupt go to the interrupt server routine, they don't want to do anything. They want to start to process, handle the interrupt right away. So the only way to do that is you have a shadow register, so you don't need to do any save. And when you finish ISR, you don't need to do any restore. So we introduced a shadow register extension and one of our code for them. All right, and also quality of service. I think most people probably not really pay too much attention about this, but RISC-V recently passed, well, not recently, probably over 6 months or so, extension called Capacity and Bandwidth Quality of Service Register Interface. So what it does is allow you to specify how much bandwidth, how much capacity in the shared resource to use by particular thread. So NDIS has a, we call reference implementation, not fully CVQRI compliant yet, but what we do is in the share cache, in this case is L2, we have 4 core, 16-way. We give each core a dedicated 4-way to allocate. And they run the bunch of benchmark, mostly it's kind of copy, and you can get 30% higher bandwidth than if all the core kind of contain all the 16-way. Okay, so this is part of the kind of quality of service mechanism. Right, so safety and security. Our chairman and CEO, Frank Well, are going to give a talk about safety. So here I'm going to focus on security. But what I want to say here, safety and security is one of the so-called the 4 key computing technology RISC-V enable. So security is actually a hot topic in RVI. So there's a bunch of task group and SIG. For example, for control flow integrity, there's a search task group. There's also shadow spec. There's also landing pads. Some of them is rectified, I believe. And there's a bunch of memory taking related stuff like pointer masking and memory taking probably go hand to hand. But if you take it further, there's a cherry there. And also there's a bunch of table-based protection or memory attribute task group or fast extension there. And one of them, going to mention that later, IOPNP, which is quite important for the trusted executing environment. And there are also countermeasure for side channel attack and other mix and then more stuff. So, but in our, certainly there's many things which are important, but what we hear most when we engage with customers is whether you have something comparable to ARM's trust zone, right? So I usually tell ourselves, you have to say we have something better. We only have something better, okay? So trusted executing environment is what? Data integrity, code integrity, confidentiality, and so on. Okay, so why do we have something better? NDIS has a security framework we call NDIS Sentry. So our T solution is like this. So from the middle, secure boot. So you provide secure boot to bring the first level of boot code from the customer, and then and that boot code kind of bring up the security monitor. It provides different zone isolation and also can load different application. And that secure monitor had 2 different versions. So there's an open source version called Opt, which kind of work together with Linux. And this just released a version called MCU-T that from the name you can tell it's basically from RTOS or work with bare metal environment. So this secure monitor is the software to provide the isolation environment for the application and for any software involved. Even in ARM Trust Zone, they have hardware level secure, non-secure, but you still need the software to enable that. So that is something like secure monitor, right? So RISC-V can just do everything together. So how do we do that in hardware? So on the bottom part, we have NDIS core and our secure platform. In the core level, a bunch of other features, but most important one is PNP and ePNP. Enhanced PNP covering everything you need in the processor side. In the SoC part, because RISC-V core, you have PNP and ePNP to regulate processor access. But in the bus component, if there's a bus master, the access, if you cannot regulate it, you cannot check it, it can cause you trouble. So that's why we have reference platform where all the device, all the memory, all the kind of subordinate has IOPNP there, so that you can so software can program it to decide who can enable, who can access the component that it's got. Certainly, you can have one PNP at the very top, and then everything underneath will be covered. But if you have too many of, if you have too many of devices underneath, you need to do fine-grained partition, and that IOPNP might be too big. So that's why where to place IOPNP is up to SoC. So there's a lot of information there, right? So and last is the general purpose application processing. By here, I mean application control processor or MEM processor for those applications, like personal computing, like smartphone, tablet, notebook, all the way to PC server, data center server as well. I think those are quite large number, but the software ecosystem actually is quite big to kind of conquer. But there's also other area which I think easier for RISC-V to kind of get in. And RISC-V already take place there, like AI machine learning, platform, multimedia, networking, industrial. So what is needed is really a high performance Linux capable processor and very good ecosystem support. And to encourage the ecosystem to do it more efficiently, so RISC-V come up with a profile. So like RVA22, RVA23 is a good profile for the software vendor to work on. And the key component like various Linux distro, like Android AOSP for multimedia, and OpenWRT for networking, and Debian for industrial. And certainly there are many other different scenarios that you can use. And other than RVI, RISE is a focus organization where NDIS also played a big role there to focus on what the above ecosystem so that the members most interesting, the ecosystem, the software part would get formed ready sooner. All right, so for that, we also can talk a little bit about NDIS roadmap for picking processor. So we have X65, which is the core balance, auto-order core, 13 stage, 4 issue, Linux capable, multi-core, and so on. It's RVA22 Plus. So I think it developed before RVA23 is concluded, so it doesn't support vector yet. So now we are working on RVA66, which we're adding vector and other stuff like hypervisor and so on. So it will be RVA23 compliant. And the performance from 66 over 65 will be like 15 to 20% up in terms of spec in. And also we have 67 kind of on the horizon for the next project, because we see it's after RVA23, there's a new RISC-V extension already come up. And we reserve a spot for X63, that's for more power optimized version, but we leave it as customer-driven spot. So we not initiate that unless the customer has special interest. and the far right one, we have the Cusco series, which is have performance another level up. It's about 50% to 2x over X66. So reason because it's designed as a 6-way and 8-way order machine, so you can configure based on the requirements. So, and other functional features, RISC-V extension is similar. So hope we're going to ready to discover more information about Cusco very soon. All right, so concluding remark. So RISC-V whole computing devices, right? so NDIS had been contribute its own part. And we have over 30 RISC-V core, from tiny core to RVA23 capable. It supports all the RISC-V standard extension relevant to the particular core. And also we automate the RISC-V custom extension with our ACE. And so we talk about a couple upcoming product, X46 MPV, X66, Cusco, and also we're working on automotive, so D23 SE will be the one coming on the horizon. We talk about IOPMP-based security platform. That's very important if you care about T or you think about ARM's trust zone replacement. And certainly our software type of release, like NDSI General Tool or kind of NDS AL software, will kind of release continuously. So, and also the enabling key computing technology by RISC-V, AI machine learning, embedded real-time processing, functional safety and security, and general purpose application processing, right? So I think with NDIS rich experience and custom experience, I think we match RISC-V's vision quite well. So we hope to bring the RISC-V to all computing devices and billion SoC at a time. Right. Okay, with that, I conclude my talk. Thank you.
Thank you, Mr. Su. Do you have any question to Mr. Su?
ご質問のある方は挙手をお願いします。
While everybody's thinking, I'm Kawasaki from RISC-V Alliance Japan, and while people are thinking about the questions, I'm going to ask this question. Between like the AX44X series and then the AX6X series, are they like primarily microarchitecture different or architecturally different? How
46 and 66 are quite different. So here, I hope you can see. So 46 is, 46 is complete in order issue, A stage, dual issue, actually dual issue, and later we might enhance it, but basically in order processor. And 60 series, starting from 65, 66, and so on, they are out of order. So it's wider, like 4 issue, and so on. So there's quite difference here.
How about architecturally, that are they different too?
By architecture, you mean the ISA, they are completely the same. So we support all the RISC-V extension relevant to the application. Like for example, if you support, you want to run Linux, all the Linux related one will be there. But you only, for example, we have the code starting with N is for embedded. So some Linux feature not needed, so you can reduce it. So basically, all the code has all the relevant feature. It's just at different performance level, right? So we always want to catch up the latest RISC-V extension. Yeah.